I've never been more encouraged about the future than I am today. And I'm not going to guarantee that by the end of this talk you will be more encouraged. You may or you may not be. That's going to be up to you. But I hope very much that you will have a deeper understanding about why I'm encouraged. And, you know, I can just tell you that I'm encouraged, and that's like giving somebody a fish to feed them for a day. But the reason that I put all of the stuff together that I'm going to be sharing is so that I'm really teaching you how to fish in terms of my understanding of this. So let's get into it. The heart of this presentation is looking at where are we in history. And in some sense, we're going to be looking at our own time as if we were historians a few hundred years in the future, imagining that we could take that kind of big frame look at where we are now. And we'll begin to do that by looking back in the past. And we're doing this so that we can have a better sense of how to work with the momentum of history. Because we need to understand that momentum in order to do that. We're going to start, however, with a little bit of the systems literacy, because there's a crucial systems concept in order to get into the understanding of the past 16,000 years. And it's something that I call system domains. I actually haven't found any place in the literature as common as this is where this is really discussed. So what is a system domain? I'm going to give you a kind of verbal description, but then I'm going to give you some examples. Don't worry too much about this initial verbal description. The examples will make it much more understandable. A system domain is a region in the relationship between the system and its context where the system has a characteristic set of behaviors. And the behaviors can change dramatically as you move from one domain to another domain, even though it's the same system. Okay, let's look at an example. H2O. Okay? We're familiar with H2O as a liquid. And imagine for the moment that that was the only form of H2O that you'd ever experienced. And you started warming it up. And you got it up to the point where it boiled. And all of a sudden, H2O behaved in a very, very different way than it had at 99 degrees C. Huge change over a very short distance. We can go in the other direction, and it becomes solid. Again, very different set of behaviors, but it's the same molecule in all those cases. It's just the relationship between the molecule and its context, in this case it's the temperature, changes. I also want to point out that this looks pretty mysterious from the surface. But if you understand the atomic physics, you can actually sort it all out. So this idea of system domains doesn't say that you can arbitrarily do whatever you want. But it does alert us to the way in which things can change very dramatically, even though it's the same system. So I'm going to turn to another example now of ecosystems. The system is going to be a forest, and the context will be the resources that the forest draws on, the sun and the rain and the soil. And we're going to start with bare ground and then watch the forest as it develops over time. So we're going to start with something that looks like this. And if we watch, so this is time down here and the ecosystem biomass going up there. And if we watch initially, it has this rising, almost looks like exponential growth curve of the biomass. But if we keep watching it, the curve turns over. And it becomes something that looks like this. That's the whole river rainforest. So it's old growth forest. So what is this? It's something that's called an S-curve, and it shows up all the time in biological systems, and in fact any systems that have the capability of growing but depend on some resource in order to grow. Why does it turn over? Well, in effect, it runs out of resources. It encounters something that is called the carrying capacity of the ecosystem. Now, I've got this curve just sort of coming in under the carrying capacity. In fact, as we'll get into when we talk more about systems, it can overshoot. And overshoot can cause you all kinds of problems, and we are in overshoot. But for the purposes of what we're going to deal with right now, it's sufficient to just do the S-curve. The S-curve has a midpoint. Below that midpoint, things are reproduction limited. That is, things grow as fast as they can reproduce because they're not limited by the resources. Above the midpoint, it's resource limited. And there are two distinct kinds of species on either side of that. You get what are called pioneer species in the reproduction limited domain, and you get succession species in the other domain. So one of the things that's interesting about these two sets of species is that their success strategies are dramatically different. They're kind of mirror images of each other. I'm not going to go down through this whole list, but just say the top 4 are exactly what you would expect for something that's based on resources. But the bottom 3 get a little more interesting. Diversity, and I'm going to, let me just go down this side here for the succession species. Diversity among succession species is high. Lots and lots of different ones of them. The complexity within each organism is also high, and the relationship with other organisms has a lot of cooperation in it. There's a lot of symbiosis in old growth forests, in places where you have the dominance of succession species. That may just apply to us, but I'm getting ahead of myself. So just to summarize this stuff about system domains, it's created by the relationship between the system and its context. Transitions can be sharp like it was in the water case, or gradual as it was in the ecosystem case. The system behavior changes across, even though it's the same system, the behavior changes dramatically. All has to do with tipping points and stuff like that, but we won't get into that right now. And if you know only one domain, if we only know one domain, we can be misled into thinking that we understand the system. And this is really important in human systems. And my favorite example, because I come out of the sciences, is what happened with Newtonian physics a little over 100 years ago, when quantum mechanics and other things and relativity were coming along. And the Newtonian physicists said, this is crazy. We know everything about the way the world works. And it was true that they had a really good knowledge of things that went slower than the speed of light, and of things that were bigger than atoms. But when you got into those other territories, those other domains, Newtonian physics just fell apart. So discovering a new domain doesn't necessarily invalidate what you have known, but if you really want to understand a system, you've got to understand what its domains are. Otherwise, you will be misled into thinking that you know more than you actually do. Okay, so where are we in history? I'm going to start with 1900. Then we're going to go back 16,000 years. And then we're going to look forward beyond where we are now into the 21st century. But we start here. And I want to just give you this graph of world population. You're probably going to be familiar with it, but I like world population because it is a wonderful indicator of what's happening for the average person. So that's the way population has grown basically since 1900. And you've heard of the idea of exponential population growth. And down here, it actually does look sort of exponential. But that's the S-curve that fits through that line. And the midpoint happened at about 1990. So we're 25 years past the midpoint. I mean, it's really clear now from the global population statistics that we are past the midpoint of this S-curve. Now that the rest of the S-curve isn't necessarily a sure prediction for where we're going, but anyway, we'll get back to that. So if we put the pioneer and succession species up there, then what that tells us is that pioneer strategy should have been the successful strategy up until about 1990. Now, how many people in this room were born before 1990? Okay? And how many of you were educated by people who were born before 1990? How many of us have worldviews shaped by the pioneer species time? Essentially all of us, okay? But the reality around us is that we have already moved into succession species time. But because we're humans, we haven't caught up with ourselves yet. So you may say, curve fitting, cool. But what evidence is there that really we are, in fact, running into resource limits? And this is one of my favorite ways of illustrating that. This is the ecological footprint. How many of you are familiar with the ecological footprint? Let me see. Not everybody. The idea of the ecological footprint is to look at how much land is required sustainably to produce the food, this is the area required for the built environment, the area required for food, fiber, and timber, and this is the area that would be required for forests to absorb the CO2 that's coming out of the burning of fossil fuels. You notice that if this thing weren't here, the curve would be a lot lower. Anyway, nevertheless, this is the reality of what we as humanity have been doing, and at about 1970, we crossed over the world's biocapacity for sustainable living. And that's one of the reasons that we are having climate change is because all of this CO2 is not being taken up by forests, but it's just going into the atmosphere and raising the level in the atmosphere. This is all part of what I like to describe as the limits to growth challenge. Just one example of that. And that is that non-renewable resources are finite and they get more and more costly to produce. And yet we've built a society that's dependent on non-renewable resources. Renewable resources can go on for a long time, but they have maximum sustainable yields. And we've pushed ourselves beyond that in things like fisheries and other places. There are natural waste processing services like absorbing CO2 with forests, but other things of that sort that also have maximum sustainable yields. And we've overshot in all these areas, but time lags of various sorts are keeping us from feeling the full impact of that. Now, I want to make the point that all of this is just because of the way that we happen to be doing things. I like to say there are no environmental problems. There are only environmental symptoms of human problems. And to illustrate that, here is a plan worked out by Mark Jacobson, who is a professor at Stanford. And he and his colleagues now for a number of years have been putting together how do you get to 100% renewable energy. And they did this for the globe, and then they backed off and started doing it for various US states. This one happens to be Washington State. And I would point out that they were starting in 2010, but in 20 years' time, you can go from a place where you have 25% renewables here in Washington State because of all of our hydropower to 80% renewables. And then another 20 years and you're at 100% renewables. We could be moving there quickly from a technological point of view and an economic point of view. This is all worked out in terms of the economies of and using existing technologies. There's nothing fancy here. It's all doable. The obstacles are human. So, world population, and just to put in this business as usual carrying capacity, which we crossed at a little bit below 4 billion back there at 1970. So as you can see, the curve is well up above the business as usual carrying capacity. However, if we weren't burning all that fossil fuel, this carrying capacity line would actually be well up here. So what about this part? What's going to happen with that? Since we're in overshoot, and this is my sense of the best guess as to where this is all headed. This comes from Jorgen Randers, who was the third author with Dana and Dennis Meadows of the original Limits to Growth study. And he has a book called 2052. And essentially, he has world population peaking in 2040 at about 8 billion. We don't know, but actually I think this is a fairly reasonable scenario. And the shift from a rapidly rising population to a population that's leveling off and then declining will have huge repercussions in every aspect of society. This is not the stuff that people are wringing their hands about right now, and yet this is the stuff that's going to really impact us out at the time frame that we still have time to influence.